Alright, electrochemical cell potential example 2. So find the potential of the cell where the reaction proceeds. So in this particular example, they've already given the overall reaction, right, which continues to the side. They've already given the overall reaction. Right? And from the look of things, we can already tell our anode and cathode. So they've given it already, which will mean that we have a. So let's look at it very well. This is the one is in the solid form, and now in the end it's oxidized, and you're seeing proceeds in that direction. That will mean that the Ni is the anode, the nickel is the anode, and then the tin is the cathode. Right? They've already specified that based on what they've given us. The reaction concentration, nickel, and of tin. Yeah, so this is what we have. They want us to predict whether the reaction will proceed from right to left or left to right, right? Basically, we're trying to find the cell potential. And then we know clearly that this is not standard condition because one of the conditions is not met, where we have here because we have the concentration of the species not being equal to 1. So clearly we know this is not standard. There's non-standard condition. So we have to use the next equation, right? So that will mean that we are using this. And because this case, let's say we are using the Oxford method, right? I mean, you have this, and then we have E cell, E standard of the cell. So let's see, E standard of the Oxford, then we have a plus, right? Okay, plus, and then we have a 0.059, and then we have log, and then oxidize state, reduce state, right? Okay, and because of that we are maintaining this plus here. Why? Because we are maintaining them in their reduced form, as we are saying, right? So if you are trying to find let's see, the potential of the anode, right, that will be, so here we are using nickel and tin, right? So nickel is right here, and then tin is here, right? So let's see. So we know our anode is, from what they've given us, our anode is the nickel, right? So the standard potential for that is minus 0.25. We have a plus 0.059. Clearly, we know the electrons involved are 2, right? Because we see the charges here. 2 plus, right? Electrons involved are 2, right? And because you are doing it for nickel now, you have log the oxidized state. So let's see. Basically, we have nickel. Let's write the equations out. Nickel 2 plus 2e minus Ni, and then we have Sn, this 10, 2 plus 2e minus is equal to Sn, right? Okay. So the oxidized state is this, right? And we've been given the concentration for that, which is this, which is 1.3. So we have 1.3. Here, remember, we are doing it for the anode, right? That's why we have EE here. And then in the reduced state is this. If it's the reduced state is this, the solid form. If it's that way, the concentration of that is 1, right? Yeah. So let's move this some. Okay. So now we have it for this. Right, so let's check what we have for that. Alright. So it's always important that you understand the principles and then you choose the method that you want to use. Right? At this particular moment, you are trying the Oxford method, right? Just to see how far that will get us. So we have minus 0.25 plus 0.059 on 2 electrons. Then we have log 10, and then here we have 1.3 on 1, which is the same as 1.3. And that gives us the EA, potential of the anodic half of the cell, to be minus 0.2466 volts, right? And let's see what we are getting for the cathode, right? The cathodic half. Here we're considering thin, right? So that'll give us, we have the value right here. That's minus 0, just this, we have it here. Okay. That's minus 0.136. We have plus 0.04. Electron symbol, that 2, still 2. Then we have log. Okay, in the oxidized state is Sn. We've seen that here already, right? And that one, the concentration is 1 times 10 to the power 4, 10 to the power minus 4. That gives us the same as 10 to the power minus 4. Let's try that one. On 1, yeah, on 1, still the same. Right? These are concentrations. If we found them, we can take these out. Oops. Okay, so let's see what that gives us as well. So we end up getting minus 0.136 plus 0.059 2 log 10 to the power minus 4, and that gives us minus 0.254 volts, and that's for the cathodic half, right? And because of how we've been doing and what we've seen, that will mean that the E cell non-standard is equal to E cathode minus E anode, right? And what does that give us? The cathode is minus 0.254. The anode is minus 0.2466, and that gives us minus 0.0074 volts, right? And because we are getting this, we are getting the E cell to be negative. Yes. Right. The question wants us to predict whether to go from left to right or right to left, right? Okay. And then we know that G non-standard is equal to minus NFE non-standard, right? And because E is having a negative sign here, that will mean that in the end we end up getting G delta G, which is free energy, to be positive. And if it's positive, it means that this direction that they've given us, which is this one right here, this whole thing from here to here, won't be feasible. So if it's not feasible, then it won't go from left to right as we are seeing here, right? But to rather go in opposite direction. So it won't go in the direction that they gave us, but to rather go from, it won't go from left to right, it will go from right to left, right? Yeah. So in the end, it means that since E is negative, that will mean that reaction will proceed from right to left. Therefore, reaction proceeds from right to left. Right, so that's it.